Hey, let's jump right into our example for section 9.2, learning Anova with a theory-based test. So in this example, we're wondering about similar to the example we had in 9.1 where we had that funny paragraph and the picture and whether they saw it or not. Well, now we've modified it a little bit. So it's the same setup, and it's the same data actually, but it's 2 hours later after the students had rated their comprehension. The researchers asked the students to recall as many ideas from the passage as they could. So it's a question of what did they recall, and the more ideas they could recall, the better score they got. Okay, so as you'll notice, the data looks similar to what we had before, but not exactly the same. But the people who saw the picture before, their recollection scores appear to be higher than the other two groups, but now the top and bottom group appear to be a little bit more different. So it's similar data, but it's not the same data. It's a different set of data based on how many ideas they could recall, and I think they scored them from 0 to 10. All right, and what I want you to notice is when we look at Anova, this testing multiple means to see whether the means are different or not. When we did the groups that were, let's say this is our data here, here, and here, and the mean is this, this, and this. Well, if we did the mad statistic, we just compare how different the means are, how different the means are, and how different the means are. Well, this data here has the same three means. So the mad statistic would be the same for this set of three data things and this set of three data. Well, these are clearly different. These have a ton of overlap and these have very little overlap. So this should be much stronger evidence that this group is different from this group is different from this group than this one, but the mad statistic doesn't find that, right? So that's where we need to go to something else, and we're going to go with the F statistic. So here we're going to see, because it takes the variation between groups and divides it by the variation within groups, if the within group variation is smaller, we're going to get stronger evidence, and that means a bigger F statistic. So our hypothesis is all three of the long run mean recall scores for students under the different conditions are the same, or there's no association between whether and when they saw a picture and what their recall score was. And the alternative is no, it actually does matter whether they saw the picture or not, whether they saw it before or after. So there is an association, or the long run mean scores are, at least one of them is different. Okay, let's check the validity conditions. So we need 20 in each sample. We've got 19. Okay, so that's close to 20. So that's, remember it said it could be 20 and not skewed, or it could be close to 20 but not a strong skew, or not a nice symmetric data. And this data here is nice and symmetric. This one's pretty nice and symmetric. But this one, look at the skew left on this. So I would say this data set is not really satisfying the validity conditions. It's not big enough, and it's skew left, so that's a problem. The second condition on the variation, well, the standard deviations are 2, 1.8, and 1.4. So yeah, the biggest one and the smallest one, if you double this one, that's more than this one. So this is fine. The standard deviations are all close to each other. All right. So now we're going to run the Anova test on the recall data, and we'll see how the mad statistic comes out and how the Anova test comes out. So to do that, we're going to jump into our applets. We're going to go down here to chapter 9, the recall data. We're going to copy that up, and then we're going to go back to multiple means applet right there, clear it, paste it, use data. There's our three groups, and we can see the three box plots. All right, and these are the summary statistics, shows us the means for each group and the standard deviations for each group, and it even computes the mad statistic for us, 1.93. And so if we go to shuffle options, we could, simulate, randomize the data into the three piles, calculate the means, calculate the mad statistic, put a dot on the graph. Do it again, do it again, do it again. Do it 100 times, do it 100 times, do it 100 times, and we'd get similar data to what we had before, and you could see how 1.93 is what we had in our actual data. 1.93, count it up. Okay, the p-value is 0, so we've got strong evidence that at least one of the 3 long-run means is different from the other 2. Okay? But this is really not what a professional statistician would do. They would not use the mad statistic. They would use the F statistic. That's what real statisticians use because it factors in not just the differences in the means, but the standard deviations and the sample sizes as well. That's very important. Okay, so it runs a whole calculation for you. The F statistic is 12.67. It will run the null hypothesis for you with the F statistics. You'll notice it looks a little bit different. You can even overlay the theoretical distribution on there for you. And then all we have to do is type in 12.67 into the greater than 12.67, count it up, and you see the p-value is 0. It gives you a theoretical p-value as well as the simulated p-value. And actually, we have much stronger strength of evidence. This is way farther in the tail than it was for the mad statistic because it is factoring in the standard deviations from the data. Okay, so now we've got extremely strong evidence that at least one of these 2 groups, or at least one of these 3 groups is different from the others. Maybe they're all different, I don't know, but at least one of them is different. And what I'm saying is not just the data, because of course they're different right here in the sample, but we're saying is the data we saw in the sample strong enough evidence that the true mean, if you ran thousands of people in the long run through this operation, the long run mean when it all settles out would be different from this long run mean or this long run mean. That's really what's going on. Once we have strong evidence, and you can click this Anova table right here and it gives you the p-value. And the way it computes this 12.6, that was our F statistic, is it takes the differences between the groups, right? 6 and 8 and 5 are different from each other. It runs that through a formula to generate this 40. And then it sort of averages these standard deviations together using another formula, and that gives us 3. And when you take 40 divided by 3, you get that 12.6. So it's looking at the differences between the groups divided by the differences, the variation within the groups, and it calculates those separately, and the F statistic is that ratio. Okay, p-value is that. So then you can run the confidence intervals. Because we have evidence that at least one is different, then you can say, well, which one is different? And it turns out they're all starred, which means they're all 3 different from each other. Which means we expect that seeing the picture after and seeing the picture before, in the long run, those means are different. Seeing the picture after and seeing the picture not at all, actually those means are different. And seeing the picture before and seeing the picture not at all, those means are different. And what we're talking about here is the recall score between 0 and 10. 2 hours later after they ran the experiment, how well did they recall it? And one interpretation would be is the long run, we are 95% confident that the long run average recall score after seeing if you see the picture after you read the paragraph, is between 4.05 and 1.74 points lower than the long run comprehension score for people who saw the picture before they read the paragraph. And that's a way to put it in context. Let's jump back to the slides. We've done the simulation, we've done the theory based, we've gotten the results. We got the confidence intervals here. We can actually conclude that this mean is different than that one, and that one's different than that one, and that one's different than that one. All 3 of them are different because we rejected the null hypothesis. At least one was different, and the follow-up confidence intervals tell us which ones are different. And then that Anova output, we saw that. This is what professional statisticians would use as an output like this. Using a proper statistical program. Of course, we're using the applets because we're just learning, but if you want to go on and take more statistics, that's where you'd go. And then the strength of evidence, just finally noticing, you know, the bigger the sample size, the stronger your strength of evidence you're going to have because of the way the F statistic is calculated. And also, the farther the sample means are apart from each other, the stronger your strength of evidence. The bigger the standard deviation, the weaker your evidence. You'd want to have smaller standard deviations so that you can strengthen the evidence. And then those factors are contributing to, the strength of evidence we've had in this example. All right, so hopefully that gives you a nice example where we kind of went from stem to stern through the whole thing, did the inference, we did a simulation and the theory-based actually in one package deal there, and you should be good to go to answer your questions now as well.